Hello everyone. My name is Dr. Vitawat Sittakul, uh, the head of Beyond 5G Innovation Center, King Mongkut University of Technology, North Bangkok. Today I would like to thank for a section chair of ITC CSCC tutorials to allow me to have the tutorial course today with everyone. So the title of the tutorial will be Simulation and Implementation of 5G System for Academic Research. In this one, we will talk about the outline, outline of the tutorial. We will start with Introduction to 5G. What is the 5G and why is this important? Another one, we will talk about the 5G architecture. What is the 5G system is and what inside. Then we will talk about how to do the coding on MATLAB, which is the very famous software simulation software around the world. And another one is for coding, encoding, and decoding on MATLAB. And also we will talk about how to use HDR, which is the software defined radio, using LabVIEW. So the LabVIEW is another kind of simulation software similar to MATLAB, but it is in graphic so that it can be very easy to implement it for 5G. And then we will talk about the system implementation using the SDR. So the tutorial course today will be how to use LabVIEW and MATLAB to simulate 5G system. Okay. So if we talk about introduction to 5G, 5G is now using in many countries. There are 715 commercial launched in LTE advanced networks in 208 countries and 182 operators in 78 countries that have launched, demonstrated and testing to use 5G. And then 74 telecom operators in 43 countries have announced this to use a 5G network between 2018 and 2022. And this is the map of how the 5G was launched around the world. So you can see that in 2022, there are many countries gonna use 5G system. So in order to do so, if we are the university and academic, how can we handle to understand 5G system? And this is the photo of the 5G system. For 5G system, they have two networks. One, they have to be working with 4G LTE. Another one they can do in standalone. There are three major technology. One is EMBB. Another one is URLLC, ultra low latency, and MIoT. So that means you can talk to many massive IoT devices. So they use many kind of the technology like FD-MIMO, carrier aggregation, dual connectivity, CV2X, connectivity and low latency, power saving, and also increases coverage. So the frequency for 5G will be around 3.5 GHz. That will be commercially dominant. Then they will add in with the millimeter wave frequency, which is 26, 28, or 39 GHz. That will be depending on what country gonna be used. And the thing that we can use 5G is also 5G will require cloud network. For cloud network, they're gonna use many kind of technology to connect into the same storage that is we call cloud network. So we will use M2M, massive, many machine to machine, and then we can use D2D device and V2X, which is something about vehicle to everything. That means you're gonna use the car to drive on the street. automatically. So in 5G, there are three main things that gonna be increases from 4G LTE. One is a massive IoT. We call MMTC, massive machine, which is a type of communication. So you can talk to many kind of system and many devices. For example, you can talk to GSM, LoRa, 6B, wireless LAN, Bluetooth, Cat-M, NB-IoT. Many kind of device can be used in the same system. So we call it diverse ecosystems. Another one is EMBB. EMBB is very easy to understand. It's something that you can increase the speed and the bandwidth. And that's why they're gonna require 3.5 gigahertz frequencies, which is very important to increase the bandwidth because this frequency can use for very high speed internet. And also the last one is URLLC, ultra reliable low latency communications. This is important from the 4G LTE because 4G LTE has some problem when the vehicle drives so fast. Let's say like the railways can go for the speed higher than 300 kilometers per hour. If you use 4G LTE, you cannot handle with this kind of speed. But for 5G, you can also connect to use the mobile phone in very high speed, like more than 300 kilometers per hour. So this is the new technology. And also this one can use with V2X or vehicle to everything. In that case, it will be very compatible to the mobile station. And this is also another application that you're going to use for 5G. One you can use for gigabyte in seconds, so that means you can go for EMBB. Or maybe you can use for smart home or building. You can connect to many devices. Also, you can use for smart city. With the smart city, you can have many kind of sensors connected together. And for ultra low latency, it will be better to use with the self-driving car or mission something that very critical, and also something about the military. When we're gonna have a war, you will have to use the mobile station so that the 5G device can be or 5G station can be integrated into a vehicle and move it and then command for the military. Also, you can use for 3D video, ultra high definition screens, or maybe you can use on the cloud service. So this is why 5G is important. Another thing for 5G that was developed is they're gonna use many kind of frequency. Not only one frequency, but can be many frequency because they have some problem with the 4G LTE. That in some country the frequency had been already used for some application already. That's why for 5G they have offered many kind of frequency to use, like N77, N78, and N79. So N78 is very popular, and N77 because they're gonna use frequency in the frequency length 3.T to 4.2 gigahertz for downlink and uplink. In this technology, they can use the same frequency for uplink and downlink because they're gonna use TDD technology instead of FDD. In TDD, you can use time to divide between each uplink and downlink. And then for FDD, you can use separate frequencies. So that means for FDD, you can consume too much bandwidth more than TDD. So if you can see in the future, they're gonna use TDD technology in the future. And they have two lengths of frequency. One is for sub 6 gigahertz, so that they're gonna use low frequency. Another one they use high frequencies, so they can use about 26 up to 40 gigahertz. So you're going to use N257, N259. Such as in Thailand, they use N70X for sub 6 gigahertz, and then they can use N259 50X for millimeter wave in future. Also, I told you before that they have a table for using 5G in future. In some cases, some countries they are not convenient to use the frequency that we offer about N30X. So that means they're gonna use another frequency in the table. And each frequency has different duplex mode, like FDD, TDD, and then SDL, SUL. Also for the millimeter wave, they can have many kind of frequency length to use, from N257 and 261. And for millimeter wave, they're gonna use TDD for the duplex mode. In 5G, they have many kind of new technologies. We call NR. NR comes from new radio frequency. So if you can see the NR in front of everything, so that means they're gonna use new frequency for 5G. Such as you can use NR MIMO, NR V2X, NR in unlicensed band, NR NOMA. We're gonna talk to NOMA in future, and NR over non-territorial networks, NR UE power consumption, NR positioning, NR URLC, NR mobility enhancement, and MR ADC enhancement, for example, NR SON and MDT, and many technology they're gonna use for the new radio frequencies. So if we have new technology, we're gonna have new thing we call new spectrum. So I told you before, we have a table of the new 5G. So for the spectrum, you can go for 0 up to 80 gigahertz using the spectrum frequency from the table for 5G NR table. And you can use for the massive MIMO and beamforming for hybrid beamforming, or maybe more than 6 gigahertz, and UE is expected to apply beam steering as well. When you go for beam steering, so that means you can move the beam of the signal to go up and down in 3D. In that case, you can reduce the interfere between two devices. And you can go for another one we call multi-connectivity. When we say multi-connectivity, we talk about how we gonna implement 5G into the 4G LTE. For the 4G LTE, normally we call E node B or ENB. But for 5G, we call GNB or G node B. In that case, you can use both of them to connect to the same mobile phone. Because what the operator don't have to do is to remove the 4G LTE and implement 5G only, because it will be very high cost to do so. So that's why we have to do multi-connectivity. And the new thing for the 5G compared to the 4G LTE is the network flexibility. Network flexibility is talk to something about network slicing. Normally for 4G LTE, you use only one we call one pipe of transmission. You cannot to slice the pipe or the transmission. But for using the network slicing, you can have many kind of the channel, like one channel for something for gaming, one channel for voice, one channel for the banking, and one channel for something else. In that case, you can know how much the traffic you're gonna use. That means in future, if the network operator want to know how much the Facebook gonna use for the capacity, they can measure using only one slicing. So they can know that how much the Facebook gonna take the use of the spectrum to use, and they can charge the Facebook later. Now we talk about the 5G architecture. For the 5G architectures, they are completely different from the 4G LTE. The thing that they have to do, because what they need to do is they need to divide the architecture into the section, more section. But for 4G LTE, everything is combined. If everything combined, that means if you want to operate something, they need to operate from one thing to another block, and then another block like that. They will take a lot of time. But if you split the blocks into many blocks, you can say which block gonna use for something. Like if you want to use something very fast, you can pass only some blocks. So that means you can increase the speed, or you can increase the latency of 5G. If you remember, for 5G you need to handle for V2X or something that you need to talk to something that moving all the time. So you need to have very low latency. That's why you need to split the box. In this case, you have GNB for intercell RRM, RB control, connection mobility constants, radio admission control, measurement config, and provision, dynamic resource allocation, something like this. So when you separate something, you can increase the speed. That is the key point of 5G architecture. Another one is the technology gonna be used for the 5G. One is we call MIMO array. MIMO array means you can talk to one UE or mobile phone by passing to 4 or 8 antenna at the same time. And with this kind of MIMO array, you can take the technique beamforming. So that means you can have beamforming between base station and the device to talk to. So in that case, you can reduce the interference. If you can imagine you're gonna use many devices talk to the base station at the same time, they're gonna increase the interference if you don't have the beamforming. But if you have beamforming, and you can see on this photo, the below photo, each device talk to each beamforming or beam steering. In that case, each device will not have the interfere between each other. And in the future, we're gonna use the concept of the massive array or massive MIMO. In that case, the antenna will be increased up from 64 antennas up to 128, and in future maybe it can go up to 10,024 active antenna elements. So that means one base station can handle up to 1,024 smartphones at the same time. And you can use the 5G numerology technique we call wide bandwidth, high order modulation schemes, or short symbol duration, multiple physical signal. With this kind of thing, you can talk to the antenna, and the antenna can use something like FPGA inside, and then you can use digitalized IQ to talk to the antenna and transmit to the mobile phone with the beamforming. And this is the technique that we're gonna use for the beamforming support in future. You can see this is the mathematics to use for the beamforming in case that you have antenna more than one. In this one, you have antenna up to, I think this one will be 12 multiplied by 12, so about 144 antenna at the same time, and then you can talk to the mobile phone in 5G network. So for the university or academic viewpoint, what we can do. Of course, we cannot to understand the 5G system by taking the 5G system from the operators. What we can do now, we can do something like simulation of the 5G system or 5G architecture from the operator by using the thing that we have. Like if we have device, we have radio unit, we have access network, we have transport, we have core network, and we have internet. If we have these things together, and we can define for the software to operate with every device, we can do 5G simulation model. And with this model we call private network. So the private network will take use of the radio unit, access network, and core network together. And when we can use the device for the 5G device, if we have the SIM card for our private network, we can operate 5G system in the campus or in the company or in the manufacturing. Then with the private network can talk to the network outside like core network and then go to the internet. So in part of the radio unit, the access network and core network, we have many kind of the company to use like Schneider Electric, Bosch, Rituals, and for transport you can use the transport from the H Micro, AT&T, Vapor, Telecom, Code, and Akamai. And for internet, you can take the internet from the Amazon, Azure, Google Cloud, Equinix นะครับ Okay, so if we can have many kind of companies support us, we can do something like 5G core network that gonna use in the campus or in the university. And there are many kind of company around the world that use private network. Long time ago they used private LTE network, and now with the upcoming of 5G, they can use 5G simulation model networks or 5G core network in the industry. So we approximate that the 5G infrastructure gonna be increased up to about 400% by 2030. And then we're gonna have 400,000 small cells gonna use for the private network in 2022. That means in the next year. So if we have the private network or the 5G core network to do for our own business, what we can do? We can use with the many kind of applications such as video tracking, security, camera, autonomous robot, drone, camera, smartphone, and tablet, or augmented reality. That everything can be used with the core network. So this is our plan to use and to understand and study about 5G network. That means we have to implement it into the 5G core network first. Then we can do something like optimization, and then we can try to optimize and increase the performance in the future. And for the radio unit, we're gonna take use of the SDR or software defined radio to operate for the radio network that we're gonna talk in the future in the next slides. So to overcome the problem of this, we need to have like open LAN, PLIT solution, and cloud native. With these things, we can operate core network. And this is the device that we can use for the operation of the core network. One side is we need to use for cloud. For cloud, we need to have private network management, third-party packet call control plane, or maybe some kind of some company to sell your software. or maybe you can implement your software by yourselves. In this one, we call some kind of ASOCSCU, which is a company to sell the core network. And we're gonna have the VMware vSphere for the cloud. For the edge computing, you need to have private network management, which you're gonna have third-party packet called control plane, and also the company software, and you're gonna use VM sphere. And this is different. You need to have radio unit. You need to have radio software to control. And this is an example of the device. So for the edge computing, you're gonna have switch and server. And for radio, you're gonna have the HDR software defined radio. And device you can be anything. And this one is the photos of the 5G core network. For the 5G core network, you need to have 5G core. And then this one open LAN is something about radio unit. So 5G core connected to the radio unit using the 10 gigabit Ethernet, because you need to have high speed for 5G communication. As you know, for 5G you need to have low latency, so the core network has to be optical fiber. And then when you talk to the radio unit, it will be go to the switch, and then go to the antenna, and then talk to the UE or the device. So in this project or this talk, we're gonna split two possibilities to understand the 5G core network. One is you need to understand the 5G private core network. Another one, you can have SDR to simulate the 5G protocol to talk to the core network. For the 5G private core network, what you're gonna have a core network into the private network. And in that case, you need to buy the software, or you need to implement your core network by yourself. So what core network do? Core network has to have some kind of authorization of the SIM card, so that it can allow your device to talk to the network if you have the same authorization. And that will be quite difficult to implement, because it will be something about IT department. Another one is 5G protocol. For 5G protocol, we talk about something about radio unit. For radio unit, you're gonna have multiple access technology. So normally you use OMA, but for 5G in future, they have some trend to go for NOMA. That we will talk in the future in the next slide. And 5G take use of the LDPC code and Polar code. Then we will talk about how to use software-defined radio to simulate the radio part. And now we talk about LabVIEW software. So the LabVIEW software will be the software to control SDR in this case. Now we talk about the multiple access. Multiple access technology can have two things. One is OMA, or orthogonal multiple access. Another one is non-orthogonal multiple access, or NOMA. For the long time ago, we take the technique called FDMA, TDMA, CDMA, and eventually we go for OFDMA. But for NOMA in future, in the new year, they're gonna go for IDMA or CDMA, LDS CDMA, Power Domain NOMA, and BDM and MUSA. And in future, the trend will go for NOMA. So what NOMA do? If you have the source code for QPSK, this is a simple case. you're gonna use the normal symbol merger to merge into the source, and then you put the pilot insertion, then you do the interpolation FIR filter, and then you change digital to analog converter. When you go to analog, you transmit the signal to the antenna. Then the signal go to the antenna, go to another receiving antenna. It will be received it, and then analog signal will be transmitted into the digital converter again. Then you do the dissimulation and FIR filter again. Then you remove the pilot using the pilot detection and then synchronization again. Then because you do the normal symbol merger, you have to do a normal symbol separator in order to remove the normal symbol of the signal. Then you're gonna have the original signal is a QPSK symbol 1 to symbol N. And this is we use the normal symbol. But for the OMA, normally you're gonna use symbol OMA merger and OMA symbol separator. So the difference will be only in this kind of the merger and separator. For 5G, they take use of the LDPC codes and polar codes, but because of the LDPC had been taught into many talk already. So in this tutorial, we will focus on the polar code, which is the new code for the 5G. So polar code, we will talk about what is the polar coding, what are the advantages of the polar coding, what is the polar transform, and bit channel and polarization, and the example of the polar code. So for polar coding, what you need to have is the block error correction coding, linear channel coding. This coding is invented by Erdal Arikan in 2008 based on idea of channel polarization, and it is a non-systematic code because polar code is very small and very flexible. So they're gonna use it for the uplink. For the downlink, they're gonna take use of the LDPC for because the LDPC is best if you have a very high information. But for low information, you can use a polar coding because it is a very strong and very reliability. So the advantage of polar coding is, first one is low complexity. It's very simple. It offers high hardware efficiency. It can achieve high throughput, good error correction, and used for control channel in 5G, and it achieves high capacity. This is the polar transforms in general. So you can have the general matrix. Normally the general matrix will be 1, 1, 1, 0. And this is the operators of the general matrix. We have x1 and x2. You do the exclusive OR. So it will be x1 plus x2. And then you have another one is x2 to pass 2. So this is a very simple concept. If you have x1 and x2 and then you exclusive OR, then you can do the same thing if you have more than x1 and x2. In this example, you have x0 to x7. You have x0 and x1. You do the exclusive OR for one time. And then you bypass for x1. Then you do exclusive OR again between x0 and x2. And x0 to the x4. And then x1 to the x3. x1 to the x5. x2 to the x3, x2 to the x6, like this. So you're gonna exclusive all together. So that with everything exclusive all, you're gonna get D0 to D7. Then you have if you increase the general metric from the G2, if you increase to G4, what you're gonna do? You have G4 for 110. Then you combine them together. You're gonna have 111, 1000, 1100, 1010, and 111. This is the G4, and this is the binary tree representation. How can you get this kind of the matrix? You do the same thing for G8. You have 1110, and then you execute for 3 times. You're gonna get this kind of the matrix. So you can see 10 will be increased, and then 11, and then 101, 111, like this. And this is a binary tree representation of G8. If you do the same thing, you can have the table of it. We call it big channel and polarization. This one will increase the quality of the channel. Then you do the polar code for the NK polar code. This is how you're gonna use the number of bits. For example, if you have the number of bits n equal to 2 power n, and you have message m length k bits, you have vector u for the length n bits. You can find nk at least reliable channels, and you can set those nk channels to 0, and then set the rest bit to message bits. In this case, you can have n equal to 3, n equal to 8, k equal to 4. You can have m equal to 1011. Okay, this is the operation. So once we know the concept of the 5G, or the polar code, we can understand it by using it in the MATLAB. For the MATLAB, we can get frozen bit indice and then PC bit location. You can get n, then check and set PC polar parameters, get sequence for n, get frozen GE, information bit indice set QL, and then get QL from GF, TM, and then Q sequence, so that you can get the PC polar. And this is the code to use on the MATLAB. And if we want to do everything in the same one, this is the total cost for the polar code. Then we separate each code to get n. How can we get n from the polar code? And this is the code to use. Then we can compare with the theory. Because we don't have much time, we will go a little bit faster. And this one, the theory, to do the how to check and set PC polar parameters. Now we can have the polar encoding. At the end, we're gonna get the table of the polar coding. And this is a very small, sorry for that, but this is the polar coding that we try to do on a MATLAB. Now we have some technique to get the frozen GE information bit and indice set QL. This is the code that we use. So we take the code from the standard from the ITU for the sub blocks interleaving, as you can see on this one. Also, we take use of this one into the code on the left hand side. Okay, and this is the how can we get the frozen bit vector. As you see, if we use the coding from the MATLAB, it will be very complicated because we cannot see the input and output clearly. So what we try to do in future or now. So recently, we move on to use the polar coding on the lab view. Unfortunately, for the lab view, they don't have the polar coding yet, but they have coding for the LDPC. So if we want to move on to use lab view, we need to generate the code by ourselves. So this is the very tough task for us to use LabVIEW because we don't have the polar coding before. So what we do the block diagram of the OFDM, and then we have OFDM moderation LabVIEW code, and we display OFDM program, and then OFDM moderation sub VI, how it look like. So we come back to the theory of how to regenerate the OFDM. So what we need to have OFDM, we need to generate the random bit, and then we change the bits to word, and then we change to 16 QAM, 16 count, and then go for IFFT. Then this is how to encode. If we decode, we have to do the FFT, and then back from symbol to word, and then word to symbol. Then we will get the output bit, and then we will get the error to show. And from that kind of thing, we operate and we program it using the lab view. And this one is the OFDM moderation on the lab view of that kind of block diagram. So after we have block diagram, we have to check if the block diagram is correct or not. So we have the input bit for 1,024,000 bits, and then we have bit per symbol for 4 bits. We have subcarrier for 16 subcarriers. We have FFT size 256. We have subcarrier spacing 4 Hz, and we change the dB per N0 is a noise about 0 to 15 dB, and this is the output we get. We get quite smooth with error rate, and we have the output FFT correctly for the very low frequencies, and we have the constant diagram. So this is the block diagram that we use for the random bit of the code. This is the mapping to symbol. This is the IFFT, and this is the FFT. Then we have symbol to word, and then we have output bit, and this is the bit error rate that we calculated. This is how we do the encoding of polar code. And next we will talk about how can we decode it. We have the same thing. We have polar decoder. We have successive constellation SC, and then we simplify SC, and then we do the SC list. SC is flat. Then we're gonna plot the cancellation, soft cancellation, polar decoding algorithm, and we have to use the function li. And this is how we decode the signal from the polar code. So we have the UI, which is the output, U1 to U8, and input is LY1 and LY8. Then we go for level 1, level 2, and level 3 to get the output. This is the operation circuit. We have Li coming to, and then we exclusive OR with the Li to power j minus 1, j plus 1. This is how we decode it. Okay, and this is how we decode because we have a very short time, so I just show you the diagram. So compare it between 4G LTE and NR 5G. They are different on the channel coding. For the 4G LTE, they use turbo code and convolution code. For NR, they use polar code and LDPC. For digital transformation scheme, they use OFDM. For the NR, they use OFDM and maybe NOMA or OMA. And they use subcarrier spacing, which is different. And then they use slot format, 9 format. For NR 5G, they use 61 format, and now future 256 formats. So this is how we work. We're gonna take use of ETSI TS 13X to 12 revision 15. In future, they're gonna have revision release 16. Okay, and this is the thing that we have already tried it for on the LabVIEW program. So to test that our LabVIEW program for polar code is correct, we also use the bit input, as you can see here. And this is the SDR that we use. There are many kinds of SDR in the market. One is very expensive, called Wave. This one, very expensive things, very wide bandwidth. But for the academic or the university, we can use for only for desktop SDR or large FPGA SDR. That is enough just to prove our concept. If our concept is correct, we can move on to the very wide bandwidth in the future. And this is the application of the SDR. For Wave, you can use for 2 GHz real time. For MIMO, we need to use at least 20 MHz real time bandwidth. And for X.0, 0.11 or wireless LAN, you need to use 20 or 40 MHz real time bandwidth. And for LTE, you need to use 20 MHz bandwidth. If you remember correctly, for 5G, they're gonna use 100 MHz. So that means you need to use a very high standard or Wave device to prove the concept, because the bandwidth is very high. So the key is the massive MIMO. That means you need to have SDR more than one antenna. So you need to have up to 64 or 128 antenna for the SDR to prove the concept. For Wave, you need to have a very high bandwidth SDR, and you need to have multiple radio access as well. And you need to have a wired network, many wired network. And this is the key that you're gonna use for the 5G standard. One is you need to have massive MIMO, Wave, multi-lat, wired network, and many kind of SDR. And then you can use LabVIEW to control everything. And this is the thing that we try to do on our lab. We have two of the SDR to connect to the computer and then talk to each other by using the antenna. And this is the LabVIEW program that we can use for 10,000 bit and 1 million bit per frame. To see the difference is not too much different. And now we compare between two things. One is we use the LDPC code and no code and polar code. And we can see that for very low information bits, for the polar code, we can get very high efficiencies. But for the LDPC and no code, they're gonna have worse, because for the BER, if you have something on the left hand side, that means you can get better results, because you can have a signal to noise ratio very little, you can get the same result. But for the another one, for the LDPC code, we need to have a high signal to noise ratio, but for no code, we need to have up to 14 signal to noise ratio dB. And this is the end of the tutorials. I hope that everyone will have some understanding about 5G and the how you can use this technique to apply into the research in the future. Thank you very much.